Great. So, hello everyone. We're really glad that you came here. And today we will present our project. It's unveiling the semantic essence text embedding summarization, and we did it in a company of in a team of me, Piotrowski, Dominik Wiśniewski, Busz, who is today I can say his absence. Our external supervisor from other company from QA, it was Juliusz Straszyński, and our internal supervisor that you can say that was our supervisor, it was Wiśniewski, and we are really glad that they help us. So I expect that everybody from audience know about text embeddings, role in today big data, the vector databases and everything. But the problem is in QA, in this example, that they have a lot of documents encoded, and they would really want to make the summarization of them, of clusters that they define, but without accessing whole documents from database. So our approach is to get from a cluster that are already defined with access to the encoder. Our goal is to generate a meaningful description of cluster without knowing all of information, knowing only the embedding of original text. So, how we solve this problem? On the beginning, the QA didn't want us to get their data, so we had to generate a data set by ourselves, and we get some inspect data set of scientific papers that are grouped with keywords, and we generate summaries for that cluster that we created with keywords, and we generated summaries with GPT for Omni. This is more detailed, but I will skip because we are already we have a problem with time. So example cluster is like we see here. It was some keyword like egg ornament. They are beginning of original documents, and this is generated summary from GPT-4 for these documents.
Okay, so we evaluated 3 solutions to this problem. Let me just remind you that what we need to do is to find the text which represents a similar vector to the given vector from embedding space, and we measure the similarity like usual in those semantic embedding models with cosine similarity. So let me start with the first solution. The first one is beam search. It's very classical algorithm. You probably heard about it, but I guess it will serve as an introduction to the next one. So what we want to do is to generate a text, and we can do it iteratively. We can start with an empty text, which has length 0, and then add next characters to it. And how we measure if the text is good? Well, we just encode it with our encoder, check the cosine similarity with our given vector, and we have some measure. The higher the cosine similarity, the better the text is. And generating next text could be done in a brute force manner, just appending every character on its own. But it's, I guess, stupid. We want to generate a meaningful description. And the search space with this approach is very, very big. So what we did use is a GPT-2, just a very, very known model. And after starting with, when we have the initial text, we can just see what are the next, I don't know, 5, 6 probable tokens, expand on that state, and run the algorithm further. And beam search just remembers the best, the most promising candidates, and it finds the best one. The next solution is MCTS. It is very similar to beam search, meaning that it also represents its states as texts, and the expansion in MCTS is also done by GPT-2. So we are just appending next tokens. And as a score for backpropagation, we initially used only cosine similarity, but there were some problems, obviously. What were the problems? For example, when you start generating text with GPT-2 by starting with initial empty string, the generated text is gibberish. GPT-2 just appends dots, new line characters, commas, and actually, because texts like that are out of distribution for the encoder that we use, it might happen that given texts have very high cosine similarity with our target vector, even though they are meaningless. What we also found out is that sometimes MCTS preferred meaningless texts over meaningful ones because we were not using perplexity in the score while running backpropagation algorithm. So we included that, and we also used Optuna to find the best hyperparameters for weighted average of perplexity and cosine similarity. And the last thing that we did is that we used a soft prompt mechanism. So what does it mean? Soft prompting is like a technique that allows us to find the most semantically similar continuations of given text. So after generating a few following tokens with GPT-2, we could drop some of those when we thought that they were semantically much different than the embedding, than the vector that our target vector. Yeah, and the third method we evaluated is not our method. It's from a paper called Text Embeddings Reveal Almost as Much as Text. And this is a very interesting model. What it does, it is trying to find exactly the same thing that we are trying to do, but in a different way. So what it does is it iteratively finds a vector which has a close cosine similarity with the target vector, but it works in a way that it has a fixed amount of tokens, and in each iteration it changes those tokens in a way that cosine similarity increases. So for example, here there is like a normal text, and after one iteration we get a text which embedding is closer to the target embedding, and some, maybe all, tokens change. This method works really well. I won't be talking long about it because yeah, there are time issues. But I can refer you to the paper if you want to read more. And let me just show you some examples. So, for example, at the top here, there is an example of a label for a cluster. And what was the thing that vec2text model generated is it's like a proper label for the cluster. We also passed it through GPT-4 to rephrase it, to make it even more readable.
Can you explain further why we use GPT-4?
Okay. I guess it would be best if we use next slide for that. Okay. But what MCTS here generated was meaningless. But there is also another example where MCTS found the keywords which are included in the description of the cluster. For example, technology and forensics is related to rescue. So it found some tokens which have similar meaning, but because of the fact that we are generating the solution iteratively, MCTS cannot change it. So when we use GPT-4 to rephrase it, we get a really clear cluster description. On the other hand, in this example, vec2text works really bad. It generates a meaningless label, and GPT-4 is hallucinating in this case. Yeah. And yeah, there are takeaways, but we can skip that for now.
Okay, so the thing is that I forgot to mention on the beginning, but such problem wasn't described in literature before. Okay, we mentioned vec2text model, but it does totally different thing. It tried to get the closest the original text, not the summary. So the very important thing was to find metrics to measure, because models are models, but how to measure the performance of models. So of course it was cosine similarity. For the second, it was perplexity, because as we said, we wanted to generate meaningful summaries. And the third one, it is rogue n. It's on case it's rogue 1. It's the similar. It's the measure how much percent of words. Okay, how much of words are in the original text and in the generated text. So the experiments that we wanted to perform was for the beginning to check how MCTS performs depending on different parameters, and of course the second one, the difference between models. And we can see the results. In x-axis we have a number of steps. In the y-axis we have cosine similarity from ground through. And we see that the model without perplexity, with 0 perplexity weight, is the best. In the second one, we see rogue 1 F1 score. So we see that the number of words that metric. Okay, so higher better. So we can see that with some perplexity weight, it's rising. Of course, we have perplexity, the lower is better, and we see that, yeah, with perplexity weight we have lower text. So MCTS with perplexity weight works. That is also nice message for us. And now we have models comparison, and the green one is vec2text, the orange one is BEAM, the blue one is MCTS, and we see that cosine similarity is the lowest for MCTS, the biggest is for vec2text. We see perplexity. We can see that the results are very similar for MCTS and vec2text. But of course, vec2text doesn't have perplexity weight or tools like this. And we can see that at the last we have okay, we can see, but we have to go further. So our insights, the MCTS works, the perplexity works, but it is worse than vec2text model that is pre-trained. And or summary, because the most important question is if that method is okay, if it works for practical use. And the answer is yes, but it depends, because for a big number of examples to evaluate, it doesn't have sense to use MCTS, and probably it's better to gather the data from database. But for example, for, I know, 1-2 examples for a second, and this is normal use of some databases that, for example, to explore it, it could be used. Okay, and thank you for your attention. Do you have some questions?